Friction is the resistance that one surface or object encounters when moving over another. Friction is a force that holds back the movement of a sliding object. That's it. Friction is just that simple. You will find friction everywhere that objects come into contact with each other. The force acts in the opposite direction to the way an object wants to slide. For example, if a bike wants to stop at a stop sign, it slows because of the friction between the brakes and the wheels. If you are running on a sidewalk and wanted to stop, it slows because of the friction between the shoes and the sidewalk. In our lab activity, we slid a shoe across the floor and friction acted upon it to slow down. We also learned that when we added 2 shoes, that equaled up to a larger mass, and there was more friction involved. There are different soles for different shoes for sports to provide the most or least friction. For example, in football they have spikes on the cleats so it provides more friction when they are playing in different conditions. You want the least friction in a sport like hockey so that you can slide across the ice and glide fast. A final example of friction is carpet slides. A carpet slide is a piece of plastic that you attach to your shoes so that you can skate or slide against any carpet-like surface. For this example, you would want the least amount of friction so that you can slide faster and it feels like you're gliding on ice. Friction is all around us and plays a big part of our daily lives, even if we don't realize it.
Newton's third law states for every force there is an equal and opposite force. That is why we can jump. When you jump, you exert force on the ground, then the ground exerts an equal force in the opposite direction of the force you exerted on it. In Activity 5, we learned about Newton's third law by completing an activity that has you sit on a scooter and push off the wall. The greater amount of force exerted on the wall, the farther you travel on the scooter. That is because with every force there is an equal and opposite force. Therefore, the more force you use, the greater amount you accelerate. The perfect way to show this is jumping on a trampoline. As you can see, when the jumper exerts force down on the trampoline exerts an equal and opposite force to the jumper, making them jump high. Since there's a greater range of motion that the jumper can go down, that means more force can be used, so the jumper will have a greater amount of force acted on them. Now, the jumper goes really slow, therefore they don't jump high. Less force means less height. Dunk contest!
Leathered, weathered Irish skin, beard orange as the sunset with a flag in the night sky.
Conservation of momentum principle is the concept that 2 objects in motion, when colliding, their momentum will be transferred to the other object. There is no momentum lost in a collision. The momentum is the same before and after the collision, but may transfer between different objects. Conservation of momentum also depends on the mass of an object. The larger the mass, the more momentum an object has. For example, in class we demonstrated this principle using tennis balls and a ping pong ball. The tennis ball moved at the same exact speed and collided, then once they hit, they moved backwards at the same rate and distance. The tennis balls transferred their momentum from one to another, causing them to accelerate back at the same speed. This shows conservation of momentum because what one tennis ball lost soon regained it from the other tennis ball. Another example of the tennis ball is when the rolling tennis ball hit the stop tennis ball. The rolling tennis ball hit the stop ball and lost momentum, but transferred most of it to the stop tennis ball, causing the stop ball to move forward with its momentum gained. The rolling tennis ball still had a small amount of momentum, but was still slowed down because of the stop tennis ball. Another example was when a larger mass football player hits a smaller mass football player during a block. The larger football player has more momentum, causing the smaller player to go in the direction of the larger football player. This shows that the larger the mass, the more momentum an object will have on a smaller mass football player. Conservation of momentum can be easily displayed in many occurrences like the tennis ball and the football players.
Newton's first law is in the absence of an unbalanced force, an object at rest remains at rest, and an object already in motion remains in motion with a constant speed in a straight line path. This means that obviously if a ball is at rest or staying still, it is not going to wander off without being affected by an outside force. A perfect way to show this is by using a ball on a Hot Wheels track. The ball stays still because, as Newton stated, an object at rest, which is the ball, stays at rest. This ball could stay here forever if an outside force never acted on it. In 1,000 years, this ball could still be right here, but if I give it a push, the object will start to move in a straight line path. This is because wherever the force is applied, that is the direction the object will travel in a straight line path. This ball will eventually stop due to friction and thermal energy buildup, but in a frictionless environment, the ball would stay in a straight line path forever, unless it is affected by another force. So if this Hot Wheels track was frictionless and went on for miles, the ball would reach the very end. This is because Newton said that an object in motion remains in motion with a constant speed in a straight line path. So the ball would not accelerate or slow down throughout all of the miles, and it would stay in the same directions that applied the force. The big ball has more mass, so its inertia is harder to overcome, or get it started rolling. So if I'm to roll the smaller ball into the large ball, it won't move. But the small ball's mass is smaller, so the big ball can overcome the small ball's inertia. This example relates to Activity 1 by they both demonstrate inertia. In Activity 1, we experimented with different tracks and dropped a marble from different spots. To start, the marble demonstrates the principle of inertia. If the marble were not being acted on by gravity, which is an outside force, it would stay on the track. Also, whenever the ball is dropped from its position, it would travel back and forth on the track forever, without friction in a straight line path, with a constant speed, just like Newton said. This is identical to our Hot Wheels track because in our example, the ball has inertia by not moving in the beginning, and then once it is pushed, it stays in a straight line path with a constant speed until friction stops it, just like in the example with the tracks and the marble.
The center of mass is the point at which all the mass of an object is considered to be concentrated for calculations concerning motion of an object. It is also called the center of gravity and the balance point of something. In Activity 3, we learned about the center of mass. We did an experiment dealing with objects, weight, string, and a hanger. To find the center of the object, we let the string hang from a hole in the object. Then we would draw a line down the object, following the string from each of the 3 holes in the objects with a dry erase marker. The center of the mass is the location in the center of the 3 lines. In the sport of football, players want to have a lower center of gravity to have better balance. That is because there is a greater amount of distance to take the center of mass of its base. A perfect example of showing taking a person's center of mass off its base is explaining this with a video. Joey right here, he has a higher center of mass. Christian here has a lower center of mass. It will take more distance to take Christian's center of mass off of its base, therefore taking him off balance. Therefore, there's a smaller distance for Joey's center of mass to become off balance. Therefore, it would take less distance to push him off balance.
Work's equation in physics is force times distance. Work involves a force and a movement in the direction of the force. A force of 20 newtons pushing an object 5 meters in the direction of the force does 100 joules of work. Joules is the measurement of work. Since 20 newtons, the force, multiplied by 5 meters, the distance, equals 100 joules, that is how much work was done in this scenario. The force is the act that you are doing on the object, and the distance is how far the object moved. Therefore, you could be pushing against a wall for hours on hours, and if it doesn't move, you didn't do any work. This works because, let's say I was pushing on a wall with 20 newtons of force, and the distance was 0. The equation would look like 20 times 0 equals the amount of work done. As you know, multiplying by 0 makes the answer become 0, so therefore the work would be 0. But if I'm to push this couch and it moves across the floor, then there has been work done. By me pushing the couch, it relates to work because I applied a force, me pushing on the couch, and a distance, which was the couch traveling a distance. This relates to Activity 4 because in Activity 4, we defied gravity by talking about hang time and jumping. This relates to work because jumping shows that work is done when a force is exerted in the opposite direction of gravity that results in jumping. The force was you pushing off the ground, and the distance was the height of the jump. This is the exact concept shown in my example of pushing on a wall and a couch. In my example with the wall, it is equivalent to pushing on the ground with your feet with all your might and not jumping. In that instance, there's no work done. But in the example with the couch, it is equivalent to jumping because there's a force either pushing the chair or jumping, and a distance, the distance the chair travels, or the height of the jump. Direction of the force does 100 joules of work.
but my car jet west as I drift over cliffs. The sunset, yes, it's me and myself. I needed a rest. The